the charge or having a quantum value, not quantum like quantum physics, but quantum just means countable. So he has a quantized value for the charge. And so when we talk about a charge of any particle, it's going to be an integer count of how many elementary charges there are, like counting eggs in a dozen, you know. So this brings us to another situation. What if these particles weren't just sitting there? You know, the Millikan's oil drop experiment, we just kind of like gently insert them with a squirt bottle. What if we shot them with a horizontal velocity through the plates? What then? So if I have this particle, this particle, this particle, and this particle, all kind of getting shot through, and I've labeled them particle A, B, C, D. Notice there's a label just above there. I know that F net on these guys is equal to Fg plus Fe. No doubt about it. Okay? But this vertical arrow on each of these represents the F net, the Fg plus Fe. And so as I look at the first one, is the first one a positive charge or a negative charge? On the whole, it's getting forced downwards. Assuming it's not neutral. What is it? Come on. Oh, either you think I'm a vampire or you say positive charge. Thank you for the sign of the cross. Okay. Yes. Positive. What about this one? Negative. What about this one? Boy, howdy, is it negative. What about this one? Could be neutral. Could be neutral. Yeah, maybe we'll put an N on that one. Yeah, that makes sense. All right, so A, B, C, and D slide sideways because what we have here is a force diagram, and on the right-hand side is actually the same four particles, but it's a pathway diagram. This is the trajectories of these particles as they get fired through. And of course, if there's an F net and there's an initial velocity that's, you know, V1x, remember from our projectile days? Each one of these guys has a V1x value for projectile, V initial x. Which path is which? Why don't you guys take a second, try to figure out which one is pathways A, B, C, and D. Go, do it. See if you can do it. Which one's A, B, C, and D? And you can just label them A, B, C, D. Don't worry, I'm going to give you the answers in a minute. Think about which one's going to drop off fastest, which one's going to drop off slowest, which one's going to drop off up or down, or drop off up, you know, whatever, or not drop off at all. All right, so can we get this one out of the way? Is this D? Fired straight through, honey. Which one is A? Yeah, the only one that went down. All right, and then which one is this one here, the one that curved first? C, because it's going to have the highest net force upwards, right? So greatest acceleration. That means this must be B. And people say, oh, okay. So sometimes, though, they're going to stick to the sides, aren't they? Can you see? You know, earlier there was a reading where you could read about an electrostatic air scrubber. Can you imagine if soot from a factory was fired between these two plates? And the soot, I mean, soot almost always has some charge to it because of the ionization process and how burning works and all that sort of stuff, right? Can you imagine if you blew soot through this thing, that most of the charged particle, or most of the particles are going to stick to this thing and not make their way out? And this doesn't have to be a big gap. You could literally have thousands of these things in a baffling system, like a vent system, right? And you could just blow exhaust through them and they would constantly be getting covered in soot. And then periodically, could we blow them off or rinse them off? 100% yes. What a great filtration system. Notice that there's no moving parts. This is great. Wouldn't we turn the power off before we rinse it off? Sure, nobody wants to get electrocuted, but this is a wonderful system. And the fact that there's no moving parts means that it's going to last a long time. And the fact that it's based on physical properties of matter means that there's not like a limit to where and when it's going to work really. The odd neutral particle is going to get through. But man, that's a minority. Maybe we're going to use like an actual sponge filter or something mechanical to catch the rest of it, you know? Like, that's fantastic. And so it's no doubt that's a good reason for why a ton of the industrial complexes around here and globally have this kind of filtration system. Like, this is a really good filtration system. I bet you if you buy a HEPA filter that costs a bit of money, it has something like this built into it. Maybe not. I don't know. Maybe something to look into. I need to get a new air filter. Anyway, The acceleration in the y direction is always going to be equal to F net y over the mass. That hasn't changed since our earlier days of physics. And an observation that we might make is that these are parabolic paths. See why this unit has to happen so much after all the other units? Like, we've got a lot of stuff superimposed on top of each other, right? But it is still just projectile motion, just that force of gravity isn't the dominant thing here. They just have AY not equal to AG anymore. And they're all different from each other depending on the charge of the particles that are flying through the charged plate gap. All right, so consider a single electron's trajectory through a charged pair of metal plates. All right, so this seems a lot like what we were talking about here. We've got an elementary charge just flying through the plates. How will gravity affect the electron as compared to the field forces? Well, it turns out that E fields dominate. In other words, the electric field force is way, way bigger than the force due to gravity. Remember we said once before that K is way, way bigger. Maybe I should put an extra greater than. And an extra greater than really is a proper notation. It means much, much greater than. That's the way it gets read when you read these things. Fe is much, much greater than Fg because K is much, much greater than G when we talk about electrostatic force constants versus gravitational constants. And we can talk about 10 to the power of 9 as our exponent and 10 to the power of negative 11 as our exponent. Like, being off by a factor of 10 to the power of 20, like, oh my gosh, how could you not notice? Anyway, why is the electron deflected upwards in this case? You guys tell me. Yeah? Yeah. So one answer is negatives attract. Negative attracted to positive plate. We could also have said negative repelled. Two L's and repelled? I always get that mixed up. No? Does it feel wrong? Two L's? One L? All right. By negative plate? So either way of thinking works. Or, what we said earlier was that we know that a positive plate and a negative plate, the electric field is going to orient internally in this electric field from positive to negative. You notice that if that electric charge is going to get attracted upwards, what we could say is that negative charges get attracted against the electric field orientation. Do you see what I mean by that? They get forced in a direction opposite the field orientation. If this was a proton, it would have gotten forced in the direction of the field orientation. So that's a pattern that you could notice. I'm not sure I want to put it into writing, but it's definitely something that I notice. It's something that I notice as a pattern. Yes?
Can I go to that?
Okay, yeah, absolutely. All right. So I want to think about the electron's acceleration. So if Fe is equal to epsilon q. Oh, maybe I should say this before we keep on talking about this acceleration. Since Fe is much, much greater than Fg, we're going to disregard Fg for electrons because it's just negligible. 10 to the power of 20, that's too much. It's going to get lost in the significant figures anyway. So we just forget about what gravity does to electrons. We don't care. It isn't insignificant for oil droplets because they're big. They're macroscopic things, right? We can see them. But for electrons, no. All right, so it's not that it's zero. It's just that it's so negligible. So if Fe is equal to epsilon q and F net is equal to mass times the acceleration of the electron, we could say essentially that F net, because we're going to neglect F big G, is equal to Fe for electrons. Because, as I said, Fg is basically equal to 0. So we just don't even think about it for that F net calculation. unlike the oil droplets where it's not really. All right. So then that means that epsilon q, that's the force, epsilon q, has to be equal to mass times acceleration. And if we do like a little bit of algebraic gymnastics, that means that acceleration in the y direction for this electron as it flies between these metal plates is going to be epsilon q over the mass of an electron. And we can call it m sub e for electron, just so that we don't lose track of what mass we're talking about here. Acceleration of an electron in a direction perpendicular to plate orientation. And I'm saying perpendicular too, because here I am saying AY, but couldn't these electric plates be oriented vertically? Like we could have stand this whole system on end, right? We could have had plates that were like this. We didn't have to send electrons sideways through it. We could have sent electrons vertically through it. So I just mean perpendicular to the plate orientation. Okay.